In this section, we will discuss another representation for exchangeable arrays, the so-called Dovbysh-Sudakov representation for gram-definite arrays. Let me start with the definition. We say that an infinite two-dimensional array of random variables is a gram-definite array if the following three conditions hold. So first of all, it should be a symmetric array. Then, second, R should be positive definite or non-negative definite. Okay, and this is understood in the finite dimensional sense, namely that if you take Rn to be the n by n block, then this symmetric n by n matrix is non-negative definite for all n. And finally, this array R is weakly exchangeable, in the sense that we discussed in the last section, namely that if you permute rows and columns of this array by the same one-to-one function pi, you get a random array with the same distribution as the original array. And this is for all one-to-one functions pi. Of course, the name gram-definite comes from the fact that any finite size block, it can be written as a gram matrix of scalar products of some vectors in Rn. And definite just refers to this weak exchangeability. Now let's start with a couple of examples of such arrays. So first example will be really simple when we consider a diagonal array. This will be a diagonal array with some random variables al on the diagonal and 0 everywhere else. Now, of course, the fact that we want the array to be non-negative definite means that these random variables should be non-negative. And in this case, weak exchangeability reduces to just exchangeability for this sequence, right? That if we permute rows and columns, this just results in the permutation of the diagonal, and it should be the same sequence in distribution. So this sequence is exchangeable. And by Definity's theorem, we know that such sequences are generated as IID sequences from its empirical measure. Right? So given its empirical measure, which is a random probability measure on positive half line in this case, because our random variables here are non-negative. Our sequence consists of IID random variables from this measure mu. Now, of course, this is maybe the simplest example one can think of. So next, let's consider a less trivial example. So let's consider an array of this form. So it looks like a gram array corresponding to some sequence from a Hilbert space, where HL times HL prime just refers to the scalar product. So of course this matrix is symmetric and non-negative definite. So to ensure weak exchangeability, one way you can do this is just to assume that this sequence HL is IID from some probability measure, let's call it G, on this Hilbert space H. So if this is just a fixed probability measure, you can see that permuting rows and columns here corresponds to permuting this IID sequence, and of course we get the same array in distribution. But we can notice also that this measure can be random. So we can suppose that G is a random measure. And the statement above, that this sequence is IID from this measure, is conditionally on this measure G. Now, of course, this means that this array is weakly exchangeable, because if you compute the expectation of some function that depends on finitely many elements of this array, let's say on the first n rows and columns, and you permute those rows and columns, you can first take expectation conditionally on the measure g. But conditionally on the measure g, your sequence is IID. So permuting the sequence is just relabeling an IID sequence. So you can get rid of the permutation pi conditionally on g, and then you can go back and see that you get expectation of the same function in terms of the original array. Okay, so this is obviously an example of another Gram-Definiti array. Now, of course, you can also combine two examples. You can take this Gram-Definiti array from the second example and add some exchangeable sequence to the diagonal. Right? The sum of two non-negative definite will also be non-negative definite. And in fact, they don't even have to be independent. They can be correlated. And so the main result of this section says that actually this covers all possible Gram-Definiti arrays. So this theorem that we are going to prove, Dovbysh-Sudakov representation, states that if the array R is a Gram-Definiti array, then there exists a random measure on the product of Hilbert space and positive half line. Let's call this measure eta, probability measure on product of Hilbert space and positive half line, such that the array is equal in distribution to the sum of Gram-Definiti array plus on the diagonal you can add some non-negative elements AL, where this sequence HL AL is an IID sequence from this measure eta, conditionally on eta or given eta. So as you can see, it's really the sum of two previous examples, except that we conditioned separately on some measure on a Hilbert space and on some measure on the positive half line, whereas here the random measure is from the beginning on the product of those two spaces. And just like in the examples above this, it's clear that the right-hand side here is a Gram-Definiti array, and the claim is that all arrays are of this form. Now, there are various proofs of this result. Some of the proofs are based on weakly exchangeable Aldous-Huber representation, but the proof we are going to give here, which is probably the simplest, it's based on the Aldous-Huber representation for exchangeable arrays. So the proof passes through some auxiliary array which is actually exchangeable, not weakly exchangeable. Begin the proof here by defining this auxiliary array, which will be actually Gaussian array conditionally on this array R that we start with. So conditionally on R, okay, let G be an infinite sequence which has Gaussian distribution with covariance given by our array R. And of course, since our array is non-negative definite, such Gaussian distribution exists, or such Gaussian sequence exists. Now, in fact, we will take not just one of these Gaussian sequences, but we will take an IID sequence of copies of this vector or this sequence G. We let Gi be a sequence, denote the coordinates by GLI for L greater or equal than 1. And for I greater or equal than 1, these are just IID copies of the Gaussian sequence we defined above, conditionally on our Gram-Definiti array. And the main observation here will be that this two-dimensional array that we just defined, right, since we now have two indices, we can just think of this sequence of sequences as a two-dimensional array. It turns out that this array is actually exchangeable in the sense that we described in the last section, namely that if you permute your rows and you permute your columns by different functions, one-to-one functions pi and rho, you end up with array equal in distribution to your original array. We will write this out carefully in a second, but more or less it should be clear, because first of all, permuting index I just corresponds to permuting this IID sequence of copies of G that we defined above. And then for any fixed I, the distribution of the column, which was just one sequence that we defined above, is a Gaussian distribution conditionally on our array R, and of course permuting the coordinates of the Gaussian vector corresponds to permuting the rows and columns of its covariance matrix. And we assume that that matrix is actually invariant in distribution under such permutations. Okay, maybe to write this out a little bit more carefully, let's compute an expectation of some function that depends on finitely many coordinates in this array. So let's say after we apply these permutations, the indices L and I here, I'm not going to write this here, but let's say that this function depends only on n rows and q columns. Of course, it's enough to consider finitely many rows and columns, because the above statement about exchangeability is really a statement about finite dimensional distributions. And then first, of course, we write this expectation conditionally on our Gram-Definetti array. And because conditionally we define the sequence over I to be IID, the permutation of indices I doesn't matter here. So in the conditional expectation, you can safely erase the permutation over I. And now in this conditional expectation, you just have independent copies of a Gaussian vector with covariance given by our array, just with permuted rows and columns. And because the covariance matrix completely describes the Gaussian distribution, this conditional expectation just depends on the covariance matrix. So it will be some function of this covariance matrix. And of course then we use our assumption that this array is Gram-Definetti, so permutation of rows and columns gives you the same array in distribution. It means that expectation would be the same if you replace it by the original array or the n by n block of the original array. And because this is the same function, this function was defined exactly like the conditional expectation of a function phi of several copies of your Gaussian sequence, except now we got rid of this permutation, so we can write Li conditionally on R, and of course you can go back and write this as an unconditional expectation. And so this shows that this auxiliary array G is an exchangeable array, which means that we can describe it by the Aldous-Hoover representation. So by Aldous-Hoover representation, which we called number 1 in the last section, there exists a measurable function sigma of 4 coordinates on 0, 1, such that this array is equal in distribution to array given by this function on various IID uniform coordinates. So there is some randomness corresponding to the rows, columns, and all individual entries in this array. where all these arguments are IID uniform on 0, 1. And so the question is, how do you recover a representation for the covariance matrix R given by our original Gram-Definiti array from this representation for this Gaussian sequence? The idea here will be pretty simple, just apply the strong law of large numbers. Namely, let's fix any two indices L and L prime. And then if we consider the following average, namely the product of the ith coordinate of GL and GL prime. Since we define these sequences to be IID over I, then we know just by the strong law of large numbers that this converges to the expectation of this GL1, GL prime 1. Of course, if you apply strong law of large numbers conditionally on R. Right, so for a fixed R, this was an IID sequence, so this averages converge to expectation, and of course this is just the covariance given by entry LL prime of our array R. But of course, once you have this almost sure convergence conditionally on something, you also have this convergence unconditionally, so with probability 1 over everything. Again, because if your set has slices of probability 1, then the set has probability 1. Okay, so not surprisingly, you can recover your covariance matrix from an IID sequence just by this strong law of large numbers. But then, what will be the corresponding statement for the array above on the right-hand side? Basically, it's the same application of the strong law of large numbers, that if we take averages over I of sigma corresponding to index L, and this sigma corresponding to index L prime, we can see that if you fix W and UL prime, so you only look at the randomness that depends on the coordinates I, this is just an average of some IID random variables. So you have convergence by the strong law of large numbers to the expectation with respect to the random variables that depend on I. So I will denote this by E prime. So the expectation of one term in this sequence. Say the first one. Where, let me emphasize this expectation, E prime is in V1, XL1, XL prime 1. And so again, the above convergence just follows first from the strong law of large numbers conditionally on W, UL, and UL prime. But as we said before, this also implies unconditional, almost sure convergence. And of course, since if we look here, these arrays here were equal in distributions, almost sure limits in terms of left-hand side and right-hand side will also be equal in distribution. So we can conclude that the almost sure limit on the left-hand side should be equal in distribution to this almost sure limit on the right-hand side. So this auxiliary Gaussian array has played its role. We have used Aldous-Hoover representation for that array, and now we get some sort of representation for the original Gram-Definiti array R. And the only thing that remains is to understand that this representation here is exactly of the form that we want. So in other words, we just need to reinterpret this representation that we obtained in a way that looks like the statement of the theorem. And for that, let's first look at off-diagonal elements. If you look at the expectation above, when L is not equal to L prime, these x's, xl1 and xl'1 are independent, so the expectation will be taken separately. So as a result, if we define the following function, call it sigma with index 1, which will depend on just w, u, and v. And it's just the average of our function sigma with respect to the last coordinate. And here I'm writing this average more explicitly because the distribution of x was assumed to be uniform on 0, 1. Then we can see that the right-hand side above with this index LL', first when you average in x, you will get exactly this function here, and so what will be left is the expectation in V1. And again, I'm going to write this expectation in V1 explicitly, so this will be nothing but this integral from 0, 1 of our function with index L, and this function given by the average in x corresponding to index L'. Okay, and then we took this average with respect to V1. But what is written here is a scalar product in L2. You can think of this as a scalar product between this function viewed as a function of v and this function corresponding to L' also viewed as a function of v. This is a scalar product in L2. And I will denote L2 as H. So our Hilbert space here will be L2 on 0, 1 with the Lebesgue measure dV. And then if we denote by HL this function sigma 1 corresponding to the index L viewed as a function of v as an element in this Hilbert space H. Then it remains to notice that conditionally on this random variable w, this is an IID sequence from some measure on this Hilbert space. Okay, I will denote this measure by G, and we just have to understand what this measure G is. But of course it's clear what this G is because this IID sequence is just obtained by plugging IID uniform UL into this function above. So this measure will be nothing but the image of the uniform measure on 0, 1 by this map where U becomes the function viewed as a function of V. A probability measure on this Hilbert space. But of course this G is a random measure because it actually depends on this random variable W. So once you fix W, the sequence of functions in L2 above can be viewed as an IID sequence, and we can interpret it as an IID sequence from this random measure G that depends on W. And so indeed, our off-diagonal elements now look like HL, HL', or some IID sequence from a random measure on a Hilbert space. And so what remains is to look at the diagonal elements and also reinterpret them in a way that matches with the statement of the theorem. We can notice that when L is equal to L', we're actually averaging the square of our function above. So in this case, let's define this function, call it sigma 2, where first we average in x the square of this function sigma. And so the right-hand side above for the diagonal, after we average in x, it remains to average in v. And of course, notice that because the integral of the square here is bigger than square of the integral, we can write this is greater or equal than integral of function sigma 1 that we defined above squared. And of course, in the above notation, this is just the scalar product of HL with itself. So in particular, this also shows that the L2 norm of this function HL is finite almost surely. So I didn't mention this above, but when we defined these functions HL, we said that it's in this Hilbert space L2. So here we actually checked that they are indeed in L2. But then if we define these random variables AL to be the difference of the two sides above, so in other words, integral of sigma 2 minus this integral of sigma 1 squared, which, as we noted above, is non-negative, then we can rewrite right-hand side on the diagonal exactly as HL times HL plus difference, which is AL, where actually this AL depended on UL. And we can see that this AL is some function, let's call it G, of W and UL. And so combining these two statements for off-diagonal and diagonal elements, we showed that our Gram-Definetti array is equal in distribution to exactly this representation that we wanted. Where HL was this function sigma 1 of W, UL viewed as a function of V and L2, and AL was just this function G of W and UL. And we can see here that if we fix this W conditionally on W, this sequence is clearly an IID sequence from some probability measure on the product of the Hilbert space, or L2, and the positive half line. And this probability measure, just like before, it's nothing but the image of this uniform measure on 0, 1, or the bag measure on 0, 1, by the map where U is mapped into this pair above. And so this was exactly the claim of the theorem, so this finishes the proof. And there is another result in the notes which I wanted to mention here, which is some analog of Varadarayan's theorem for empirical measures. And in fact, the proof follows pretty directly from Varadarayan's theorem, so I will not go over it here and will just refer to the notes. So let's suppose that we have our array, and instead of in distribution, let's say that it's generated exactly by some IID sequence HL, AL, as above, an IID sequence from some probability measure on the product of the Hilbert space with a positive half line. And the question here is, can we recover this measure from this array? In other words, as a measurable function of this array. But if we look at this for a second, we can see that actually it's not possible to recover this measure, because if you take some orthogonal operator on your Hilbert space, if you apply it to this sequence HL, it will not affect this representation, or it will not affect the scalar products. This means that the best we can hope for here is to recover our measure only up to orthogonal transformations on the marginal on the Hilbert space. And that's exactly what this analog of Baradarian's theorem says here. It says that there exists a measurable function of our array with values in the space of probability measures on h times positive half line, such that this measure is equal to the measure that generated our array up to some random orthogonal transformation on the first coordinate and the identity on the second coordinate on the positive half line. And this equality is almost sure for some orthogonal transformation u. Of course, here we don't know what this u is, but it doesn't matter to us because orthogonal transformation doesn't affect the scalar products. An IID sequence from measure nu prime would give us array equal in distribution to an IID sequence from measure nu. Again, I refer for the proof of this result to the notes. So this finishes our discussion of the Dovbysh-Sudakov representation and the chapter on exchangeability.